For question number 8, we need to know the photoelectric threshold. So we use this equation. E is equal to H. So this is the Planck's constant. Energy is equal to H. And H is multiplied by C, the speed of light, divided by lambda. So if you don't have the wavelength, you can get it from the frequencies as H multiplied by the frequency. So it's either the Planck's constant multiplied by frequency or multiplied by the speed of light over the wavelength. Here I'm required to find my question the wavelength. That's why I will use this one. So I'm going to use this one. And color for the E is equal to 4.19. So I'll first get the value of the energy. So if I have Planck's constant equal to 6.63 10 to the power of negative 34, and this is per joule in seconds, and the C in speed of light is 3 multiplied 10 to the power of 8, and take care this one is in meters per second, while the wavelength is found in nanometers. So what I'm going to do is that I will just use this equation is equal to hc over lambda, and then when I have my energy, so when I have my energy required to find, no, I have the energy already, and this is 4.19 10 to the power of negative 19, and then I have the Planck's constant, and I have the C, so the lambda is very easy to find. So I'll multiply E multiplied by lambda, HC, and then I will get my lambda equal to HC divided by E. So this means that my H is 6.63 times 10 to the power of negative 34. Take care of the unit. The unit is joule per second, and the other one is the C. The C is 3 multiplied 10 to the power of 8. That's meters per second. So that's meters per second. So I have 2 seconds here. This is joule per second. So the first one is joule second. Sorry, this is joule second is not down. The other one is down. Meter over second. This one is down. And then I will get my answer. And don't forget to cancel out the units. When you cancel out, the joule will be cancelled with another joule. Where is this? The joule, this is the energy. So the energy here is 4.19 times 10 to the power of negative 19 joules. So these joules cancel with these joules. The second cancel with second, and my answer will be in meters. So the remaining is that my answer will be in meters. I will get the answer and see its value. By the calculation, I will see my answer as 475 nanometer. Take care, the answer will come in meter first, but then you have to multiply by 10 to the power of 9 so that you can get it in nanometers. And then you see the range of colors. He's giving you different ranges of color. I can see that 475 is closest to the blue. Blue is from 424 to 491, so the answer is blue. Question number 9. I need to find the electronic configuration. Don't forget the basics, the output principle telling me fill lowest energy orbitals first. So don't go for up. You have to fill 1s, 2s, 2p, and then like that. Maximum 2 electrons per orbital, and they have to be in orbit opposite spin. And Hund's rule tells us to fill the orbital singly before pairing. So if you have 3 orbitals here in the p subshell, don't go and do this like that. So you have to fill one here first, and then one here, one here. If you have more electrons, you can go and fill the other ones. So nitrogen has 7 electrons. What is the correct electronic configuration in the box representation with the lowest energy? What is nitrogen is 1s2, so I have 1s2, and then 2s2, and then 2p. How many electrons is remaining from the 7 electrons? 3 electrons only, so it will be 2p3. Let's see the explanation. So the explanation is telling us simply that I have know that the nitrogen has 7 electrons to place. The first shell has 2 electrons. The second shell has 2 electrons in the 2s and 3 electrons in the 3p. So apply the rule. Don't try to make it like that. When you are trying to make the electrons, it will be 2 electrons here in 1s and 2 electrons in 2s, and then you have the 2p. So put 1 electron and 2 electrons, 3 electrons, 4 electrons, and see the number of electrons that's remaining. So see the number of electrons that's remaining. I have 3 electrons. The electrons, don't make them like that. So don't do 1, 2, 3 like that. It's wrong. You have to fill. Hund's rule is telling you that you fill first 2px, and then 2py, and then 2pz, and then if you have more electrons, you can add them. So 1, 2, 3. So don't go and do like that, and this one is not here, because you have to make the electrons fill the singly first before you start pairing, before you start adding 2 electrons together. The next question is very important. Which of the following species is considered as free radical? The free radical electron species are the species that has unpaired electrons. So if you find an S at the beginning, for example, and it's half filled, or you find that there is a P and it is half filled. Why it's half filled P? Because if you have a S, it has maximum 2 electrons, so one is half, and if you have P, it has maximum of 6 electrons. So if only you have 3/6, it will be called half filled, so it is a free radical. No, the unpaired electrons, it has to have an unpaired electrons. So see, this is unpaired. This has 3 unpaired. So if it is 3 unpaired, it's not free radical. It's half filled only. In order to be 1 unpaired only free radical, this one has to be missing 1 electron. So if you found that the last orbital that you have has 1 electron only, the last orbital in your configuration, not the first, not the second, the last one has only 1 electron remaining. So this one is not free radical. This one is not free radical because it has 2 which are unpaired. I need one only to be unpaired. So again, have a look. If you want to have a look at the free radical, if you want to have a look at the free radical, you see how is the free radical made? Free radical, if you have here like that, the last orbital of the configuration to F1 is 2, 2 is 2, 2 P6 like that. The last one only is half filled. So it is called non-paired. What is the meaning of non-paired? It means that it is 1 electron alone, not like this. This is paired, this is paired, this is paired. So you have to have one orbital only non-paired, then you can call it free radical. This is, for example, you have 3 electrons, so this is not free radical because 3 are unpaired. If you have like that, then 2 is unpaired, it's not free radical. Here only you can say it's a free radical because the last orbital is unpaired. Or if you have last orbital as S, and then it is like that, then it is not unpaired. So it is paired already, so it's not free radical. Only if it is 1 electron alone, then it will become called unpaired. And if it is called unpaired, then it is a free radical. So the fluorine is the first one that I will see it, and this is the only one. And 1s2, then 2s2. How many electrons I have? Total 9 electrons. 4 are finished. And then I will go to the 2T. I will say 1, 2, 3. So 3 electrons, and then I have 5 more, right? That's like the 4, there is 5 more. So 1, 2, 3, 4, 5. Oh, this one. This is unpaired, so it is a free radical. So this is my correct answer.